But this goes over isotopes, what we talked about last week, and we did a little work on, and we'll talk a little more about them when we get to notes.
So, you've heard about isotopes, but what exactly are they? You probably know that atoms have a dense nucleus made up of positively charged protons and neutral neutrons, and that the nucleus is surrounded by a bunch of negatively charged electrons. Isotopes are atoms of the same element, meaning they have the same number of protons and electrons, but that have different numbers of neutrons.
This is the definition I had you write down for the assignment last week, the 1130 isotopes. So making sure we know isotopes are atoms of the same element, like carbon, for example, with different numbers of neutrons, right? So they have the same amount of protons because they're the same element, but they have different numbers of neutrons. So our example here, the red dots are neutrons. So there's 3 neutrons in this isotope and 2 in this one, and they both have 2 positive protons.
The differing numbers of neutrons give isotopes different masses. Back in the early 1900s, the discoverer of the electron, J.J. Thomson, with the help of the student Francis W. Aston, identified 2 different types of neon atoms. One type with 10 protons, 10 electrons, and 10 neutrons, and then one with 10 protons, 10 electrons, and 12 neutrons. Aston went on to invent a groundbreaking machine that he called a mass spectrograph. Using this machine, Aston identified hundreds of other isotopes of other elements. The mass spectrometer is now used in labs all over the world, and Aston won the 1922 Nobel Prize in Chemistry for his work. These are the isotopes of neon that Thomson and Aston saw. The numbers you see here tell you the total number of protons plus neutrons in each atom, and they also tell you the isotope's approximate mass. Technically, the mass of an atom would include protons, neutrons, and electrons, but since the mass of an electron is almost 2,000 times less than that of protons and neutrons, we can basically ignore them.
So that number in the top left corner, when we looked at isotope notation, is our protons plus our neutrons, and that's basically the mass of the atom approximately. What he said is very true. We kind of ignore the mass of electrons. It's very, 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 very tiny in comparison, 2,000 times less than protons and neutrons. So we just kind of ignore the mass of electrons. Right, so just a little review from last week, just to get our minds back thinking about isotopes chemistry. So if you would go to Schoology in chemistry class, there's an assignment called 12-7 Nuclear Chemistry. Open that up, and there's a PDF there. Put that into Notability. If you miss something, you miss a blank or a question, the slides we are going to look at together are posted on Schoology. So you can always open them up. If you miss a word or a definition or the answer to something, it will probably be on the slides, which are posted. Okay, nuclear chemistry. Here we go. Maybe you've seen this sign before. I feel like radioactivity and nuclear chemistry get a lot of media attention. Like if you're going to put any chemistry in a movie, it's probably going to be something about radioactivity because that's exciting. Okay. Also, nuclear things make the news a lot. They're sometimes awful and terrible, sometimes pretty awesome. But we're going to talk about what's actually dangerous about radioactivity. How dangerous is it? We'll talk about all that stuff. Just a little reminder, this is a model of an atom. Of course, these perfect circles don't exist where the electrons live, but we know the electrons are on the outside, right? And our neutrons and protons are in the middle, and we call this the nucleus. Okay, our focus for nuclear chemistry is the stuff in the nucleus. Okay, kind of matches our name. We kind of, for nuclear chemistry, we do talk about electrons a little bit. We'll get there, but mostly we're focused on what's going on in this very center part, the nucleus. So a little review for us. So on your document, you have some questions and then some like fill in the blank notes type stuff. So this first one is, what are isotopes? If I have it highlighted in yellow, right? That means you are writing it down or typing it. So on your document, you are going to write down this definition: atoms of the same element that have different numbers of neutrons. That is an isotope. So make sure right here in this section below number 1, you are typing the definition, right? So we are all on number 1. What are isotopes? And you're just writing this definition of isotopes: atoms of the same element that have different numbers of neutrons. So if they're the same element, that means they have the same amount of protons, a different amount of neutrons. So this is just a little check-in. You don't have to write anything down for this part. The number of what subatomic particle varies or changes in an isotope? What is the subatomic particle we are changing between isotopes? Is it a proton, a neutron, or an electron? Which one is changing? Type it in the chat. You can unmute and let me know. Which subatomic particle is changing in an isotope? Is it the amount of protons, neutrons, or electrons?
It is neutrons.
It is neutrons. Isotopes means we're changing the amount of neutrons. The other stuff is staying the same. All right, we ready to move on? Good. Okay. Hold on. There we go. Okay. All right, so we have the isotope notation. So this is how we write out information about isotopes. We did this last week. So the big letter that you have, right, is our element, right? So whatever element we have, we used carbon a lot last time. Then the number that's on the top left is our atomic mass, neutrons plus protons. And the bottom left number is just the atomic number, the protons, the number on the periodic table. Okay? So an example. Oh, I don't know why it's not showing up here. Let me show you here. An example is here. So we have carbon. There's our element symbol. The number up here, 12, is our atomic mass. So that's how many neutrons plus protons. And our number down here on the left is the atomic number, or how many protons. So what could I do to figure out how many neutrons are in this carbon isotope? What do I do math-wise to figure out how many neutrons are in carbon 12? Okay, think about that. We'll come back to it. All right. Okay, so just take a look right here. I pulled some screenshots from our PhET simulation. So we have carbon 12 and carbon 14. So what I want to hear from you, either type in the chat or unmute and let me know. How are these two different? What's different between carbon 12 and carbon 14?
Looks like there's more stuff in the middle.
There's more stuff in the middle. Absolutely. In the nucleus, in carbon 14, there's more stuff. What is there more of? Everything in the middle or just one of the?
It looks like the gray stuff has
the gray stuff, and the gray stuff are neutrons, right? So there are 2 more of these, right? 2 more neutrons in the middle. Okay, so that changed our number up here, right? We went from 12 to 14. It's because our number up here is protons plus neutrons. So if we add neutrons, it's going to add to our mass number. Did our number of protons change?
No.
No, absolutely not. Never, never. Proton number does not change. All right. I don't know why pictures aren't loading there really well. I'm going to steal one. Okay. Okay. Give me 1 second. So on your sheet, you are adding in writing the isotope notation for carbon 12. Okay. So that's number 2. And number 3, we just talked about how do carbon 12 and 14 differ. Okay, so the isotope notation for carbon 12 is this right here. So note that the 12 matches with our mass number at the top left. So that's how we name the different isotopes, is we just take the mass number, the protons plus neutrons, and we add it to the end of the element name. That's how we know which one we're talking about. So number 2 is here, the isotope notation for carbon 12. And number 3, how do these differ? We got to the fact that carbon 14 has 2 more neutrons. Right? Carbon 14 has 2 more neutrons. Any questions about 1 through 3?
Maybe no.
No, we're good. We're ready to move. Okay. Give me 1 second. I'm going to put this picture back in here. Must have deleted something. Okay. Here's our example. Okay. So we're moving on. You have a problem that looks very much like this. So now we're going to go back to that question. How do we figure out how many neutrons are in an isotope when we have the isotope notation? So the first thing we want to do is determine our protons and our electrons. So which number tells us our number of protons in this nitrogen 15 isotope? Which number, the 15 or the 7? Which one tells us protons?
The 7.
Morning? The 7. Okay, so right away, we can add 7 for protons. So a 7 protons. And this is a neutral atom. So how many electrons, how many negative electrons are we going to have if we have 7 positive protons? Not a trick question.
7.
7, right? 7 protons. That means we need to have 7 negative electrons to balance it out. So we have 7 protons. We have 7 electrons. Okay. And then this little n with the 0 is the neutrons. There's no charge, 0 charge on a neutron. That's where the 0 comes from. How do we know how many neutrons are there? Hint, we have to do some math.
15 minus 7.
15 minus 7. This is my favorite because it's already set up, right? It's like you just put a line here and a little minus sign. So we take the top 15 number and we subtract 7. What do we get? Little math.
8.
Little math quiz this morning. 8, right? 8 neutrons in nitrogen 15. Does that make sense? You tracking? Okay, so right now I want you to practice with nitrogen 14. Fill in these numbers. Yes, Bowie.
I can't see what you're writing down.
I'm not writing anything down.
Oh, okay.
I just have a little mouse because I'm on slides. Okay, so for nitrogen 14, I want you to practice. I'll give you a minute here. Fill in how many protons and electrons, and then do a little subtraction and find out how many neutrons are in nitrogen 14. So I'll give you till 9:26, and then we'll check it. If you have time, you can go over here. This is PB. This is lead. 207.
What was the first one?
The first one, we have protons. That's our bottom number right here, 7. And our electrons just balance out our protons because it's neutral. So we have 7 positive protons, which means we have to have 7 negative electrons. So 7 protons, 7 electrons. And to get our neutrons, we take our top number, our protons plus neutrons. We subtract out this bottom number, 7, and we got 8. So 8 neutrons are left after we subtract. So 7, 7, 8 on this one. All right, it's time. Nitrogen 14, how many protons do we have? Type it in the chat, unmute and let me know.
7.
7. Oops, sorry, keep switching. 7, right? And therefore, how many electrons do we have to balance out our charge? 7, good. What about neutrons in this one?
7.
7. That one's easy. 14 minus 7 is 7. Okay, then you have this giant atom. In this lead atom, this isotope, lead 207, we have 207 little particles in the center. It's much bigger than nitrogen. Okay? So, how many protons do we have in lead 207?
82.
82, it's that bottom left number. And then how many electrons must we have?
82.
The 82, right? We got to balance out the charges. Okay, now this subtraction's a little harder. Maybe you got to use a calculator.
125.
Ooh, there we go. 125. How'd you get that, Stephanie? Sorry.
Subtracted 207.
That's right. You take 207 minus our number of protons, 82, and that's how many neutrons we have. Any questions about doing that math, figuring that out? Set up real nicely for the subtraction part. Okay, so that was number 4. Right, number 4 followed right along with that. So we should have 1, 2, 3, and 4 done. Yes? Check, check. Okay. Cool. What does this all have to do with nuclear chemistry, though? We haven't even talked about radioactivity yet. All right, we're getting there. Okay. So you've maybe seen this before. 9th grade, probably 8th grade, maybe even 6th grade. This is our light, the electromagnetic spectrum. So radiation in different forms. So what we see, the visible light, is this little section here. The wavelengths that are in this range right here are the light we see, the different colors that we see as humans. And there's all these other wavelengths we don't see. There's some that are shorter wavelengths and some that are longer. So see this little yellow box right here that I put around these labels? That is what you're adding to number 5. Okay, you are labeling the different, the order of the electromagnetic spectrum on your document. So all the way on the left are gamma rays. Then we have X-rays. You maybe have gotten an X-ray before. That's what they are shooting at your body to get a little picture. Are your bones broken or not? Ultraviolet, UV radiation. Maybe you've heard UV radiation, right? That's what we're getting from the sun. Then we have our visible light that's already labeled for you. Then if we get longer wavelengths, we have infrared. Then we have microwaves. Yes, that is what your microwave is making. It's making these microwaves to heat up food. Really, it's making any water that's in your food move around faster and heating it up. And then radio waves, which is literally how we get radio stations, right? We have these wavelengths. They're around you right now. They're in the air around you. They're being emitted from towers to get to you to be able to turn on your radio and hear some things. So you are adding in this order, this part. You should have the rest on your sheet. So there is radiation around us all the time, right? Sounds scary, but we are not, generally, we are not harmed by this, okay? We're definitely not harmed by visible light. That would be bad. These guys aren't doing anything to us. X-rays, when we start to get real short, we start to get a little damaged. Like sometimes you can't get X-rays. Like I couldn't get an X-ray right now because I'm pregnant, right? So that's not great for a growing human inside of me. It's not good. So I cannot do that. Like when I go to the dentist, I can't get the X-ray scans right now. We as not infants and babies can handle X-rays, right? We can get those, but you don't want to like hang out in X-rays all day. It's not good for you. All right, any questions about our scale here? Anyone need more time to write those down? My gosh, can you hear my cat? My cat is just whining outside the door.
No?
Oh, trying to get in. You can't hear that. It's too quiet. My cat's whining right now for food. Okay. We good? We ready? Check. I'm hearing nothing, so I'm going to go ahead. If you miss anything, again, you can get to these slides on Schoology. Okay, so radioactivity. What's that? What is going on? Oftentimes, we think of superheroes or like movies that have not actually real plot lines, right? But radioactivity is a real thing, okay? It's just usually not producing superheroes or supervillains, okay? So what does radioactive mean? The highlighted parts. Remember, the highlighted parts are what you write down. Okay, so on the sheet, you have the definition for radioactive with 3 blanks. And you are filling those blanks in with these 3 words in this order. So radioactive is elements that do not have a stable nucleus. We saw that in our PhET, that some of the things when we added too many neutrons became unstable or we didn't have enough. They're kind of like shaking around in the middle there, okay? So when that happens, when they're not stable, when they're unstable in that center, the nucleus, particles or rays are given off, they shoot out from there, from that atom, to change their nucleus because they really want to be stable. Atoms hate being unstable. They're super lazy. They want to be like calm. They want to be relaxed. They don't want to spend more energy than they need to. That is not what they like. They do not like that. They would like to spend the least amount of energy possible, and being unstable and all that like shaking and like moving around and like not being comfortable, that takes a lot of energy. They do not like that. Okay, so what they do is they send off either particles or rays. We're going to talk about both of those, particles or rays, and they just like shoot out from the middle of the atom. And that's what being radioactive is, when those rays or particles are shot out from the middle of an atom. Not the electrons on the outside, but something about the protons and neutrons in the nucleus. Any questions about that? Okay, so what we call radioactive decay, when something decays, right? It's kind of like breaking down. We think about decaying, I don't know, roadkill on the side of the road or food, right? It is breaking down, right? We call this disintegration in chemistry. So radioactive decay is the spontaneous disintegration of the nucleus of an atom. So when these particles or rays are given off, we call it radioactive decay. What does spontaneous mean? What is that word spontaneous? What does that mean? Does something make it happen, or does it happen on its own?
On its own.
On its own, right? Spontaneous means it's just happening. No one's like going in there saying, all right, you particle, get out of here, right? The atoms it's just kind of automatically doing that so that it can become stable. So that's when we get radioactivity, and when we get radioactive decay is when those atoms are trying to get comfortable. They're trying to get stable, calmer, right? They want to get rid of some stuff. Sometimes lightweight isotopes, so that would be the isotopes that are like at the beginning of the periodic table, like things with 1, 2, 3, 4, 5, 6, 7. Those are all, we call those lightweight isotopes. Some of them are radioactive, but mostly we're looking at all the elements that have an atomic number bigger than 82. Those are all radioactive. Because they're so big, right? They have these giant, well, we still can't see them. They're not actually giant, but they're compared to like helium, hydrogen, those beginning atoms, they have really big nuclei with lots and lots of particles in them. And that is just easier to be unstable then. So anything greater than 82, those are going to be radioactive on the periodic table. So if we look here, all right, we have blue. Blue means not radioactive. Okay, blue means not radioactive. Most of these beginning elements you see, and then we get to 82, and then we switch over. Green's a little more radioactive. We do have one here, 43. 43 is radioactive, and then some of these down here, the lanthanides, are radioactive also. The most radioactive ones are these purple ones. Okay, if you look here, these are the ones all the way up to 118 that we've just discovered in the last like 10 years. Okay, there's some in the red zone. Okay, some you've probably heard of, and some maybe not. Okay, we're going to talk about a few of them. Right, but these are the heavier ones are radioactive. Generally, all the heavier ones, anything above 82. Okay, you have this table now on your document. Yes? Do we all see that?
Yeah.
Okay, so we're going to go through each particle, alpha, beta, and then gamma. And we're going to go through all these sections, and it does go in order. So we're going to start there with alpha and symbol. And you're just going to go down. Then we're going to talk about the composition, the mass, the charge, and just follow those along in order. Okay? You ready? There's a little more writing in this table. So if you need to make your text smaller, you probably want to type in this section. Okay. Alpha decay. This kind of decay is, remember, decay is just changing, something's leaving that nucleus in the middle. So you start with a large, unstable nucleus, and when alpha decay is over, you have a smaller and more stable nucleus. So what is leaving are these alpha particles. So this nucleus will shoot off an alpha particle and be a little smaller and more stable. That's what is happening with alpha decay. So on your table, you have a spot to write a symbol. This is a little Greek symbol. It's not a letter we use in our English alphabet, so it might take you a second to draw that. That is the Greek letter alpha. It kind of looks like an A, but it's got a little extra line right here, right? So it's kind of like part of an infinity sign. And what is that composed of? The composition, what it's made of, that little particle that gets kicked off in alpha radiation, an alpha particle, is really just the nuclei of a helium atom. So helium has 2 protons and 2 neutrons. So to become more stable, this really big atom is like, I'm gonna get rid of 2 protons and 2 neutrons. Get out of here. We call that an alpha particle. Here's the isotope notation of a helium alpha particle, but you just need to make sure you know it's the nuclei of a helium atom. That's what an alpha particle is made out of. So those get shot off from the atom. What is the mass of the particle that gets shot out from an atom in alpha radiation? Well, helium nuclei are made of 2 protons and 2 neutrons, so when we add them together, our mass is 4. Oh, I forgot to add in, 4 AMUs, atomic mass unit. Always want our units, right? For what? 4 atomic mass units. Our charge, well, we shot off 2 positive protons and 2 neutral neutrons. Neutral don't have any charge, and protons have a positive charge, right? So our overall charge of an alpha particle is +2. Does that make sense? Okay. How fast does this happen? The relative speed when they get shot out from the nucleus, how fast are they going? Alpha particles are slow in comparison to the other 2 types. They're pretty fast as far as speed goes. They're going 15,000 kilometers per second. That is very fast for us. We cannot move that fast as humans. But as far as radiation goes, that's pretty slow. So origin means like, where do they come from? Why does this happen? Okay, so we're going to talk about fission later, but it's a fission product. So that is when 2 atomic nuclei split. And those middle nucleuses break up. You sometimes will get alpha radiation shooting off of there at 15,000 kilometers per second. How dangerous is it? Relative danger, that means like to us as humans. How dangerous is it to be hit by alpha radiation? It is most dangerous when it's ingested, we eat it, or inhaled, we breathe it in. Don't want to do that. It has a large charge and it is the heaviest, so it can cause the most damage. It's pretty dangerous. You don't want to be around it without protective gear. Okay, how are we doing on that chart? Do we have all these things done and we're ready for the last one? There's one more box to do, right? Okay, I'm gonna go on. So the last box is shielding. And we wanna know what can protect us from alpha radiation. So you see, here's our alpha ray. And what can stop them? What can stop an alpha ray? Right away we get to
Paper.
Paper or skin stops alpha radiation. That's why they said it's dangerous when you consume it, eat it, or breathe it in. But we're like pretty protected from it. Our skin stops it because they're kind of heavy, right? So all we need is paper or skin to stop alpha radiation. But if we ingest it, it's no good. Right? You don't want to be eating or breathing in alpha radiation. But our skin will stop it. So that's what you write in the shielding box for alpha radiation. All right, are we good?
So basically, if you made a underwater base, you wouldn't technically, if something was to be bombed.
I see. Yes, we will talk about that a little bit. But yes, so you're looking down here. The best blocker here is water and concrete. So you could have an underwater concrete bunker. You're like set. You're blocking alpha rays, beta rays, gamma rays, X-rays, and neutron rays. You're safe. I mean, you're underwater in a concrete bunker, but yeah. Okay. All right. That is alpha radiation. We're not going to talk about nuclear equations too much right now, but you can see what's happening. Okay, we have the original. This is polonium-208, and they give off an alpha particle, right? So 4 of the protons plus neutrons. So you see that 208 go down to 204, right? And 2 protons were given off, so 84 to 82, and now it's lead plus an alpha particle. We're not going to get too much into that right now. We will talk about nuclear equations, but after break. Okay. Here's another example. Okay, beta decay. Beta decay. The first one kind of looked like an A. This one kind of looks like a B. What's going on here? We have a nucleus, and somehow we get an electron out of there, and then our number went up. We went from carbon to nitrogen. So our proton count went up. That seems weird. Are we adding a proton? What's going on? So let's look at it. Our symbol is this fancy, weird-looking B. It's a beta. It's a Greek letter, beta. So what is beta radiation? What's shooting out of an atom when we have beta radiation is an electron. One electron getting shot out, but like from the middle. And electrons don't normally live in the middle. So what is happening? So our composition is 1 electron. That's beta radiation. And the mass, well, it's the mass of an electron, which is really 0.0005 atomic mass units. But the secret is we really just kind of round that to 0. We just kind of say there's not really a whole lot of mass. There's like a tiny, tiny, tiny amount of mass, but it's very, very, very small. We just essentially round it to 0. Our charge, it's 1 electron. Electrons are negative, so we have a charge of -1. Yes? This gets faster than the alpha particle. Relative speed, it's almost light speed. Okay, it's almost light speed, about 30,000 kilometers a second. That's like double the speed of an alpha particle, which makes sense. It's smaller, right? It's going to move faster when it gets kicked out. Okay, so where do these electrons come from? They're not from the outside of the atom. They're from the center, from the nucleus. And I thought there weren't any electrons in there. So what the heck is this? Okay, the electrons break off from a neutron, a neutral neutron in the middle. So just the negative part of a neutron leaves, which is an electron. So what's left is a proton. So those neutrons, when the negative part of it, the electron part of a neutron, gets split away from that neutron in the center and it leaves behind a proton. So that's where we get the electron from the middle, the nucleus of an atom. The relative danger, these are less dangerous than alpha particles. That's kind of what we want to say. So alpha particles, not great, but you do have to ingest them or breathe them in. beta particles are not as dangerous as alpha particles. They're not quite as dangerous, but they get through your skin. So, you know, to protect yourself, what can shield you from this radiation? A thin board, like aluminum. That is going to protect you from beta radiation. Is paper or skin? Nope, it's going to go right through it. So for the shielding section for beta radiation, put a thin board such as aluminum, or a few centimeters of air. So it can penetrate through your skin, however, is not as dangerous as alpha particles. But you do need a little protection from it. You gotta suit up, right? All right, any questions about beta particles?
No. But can you go back? I haven't done yet, though.
Oh, yes. Okay, so it is 9:51. I see that. I'll hold this slide up here if you need to take notes, but always, 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 these slides are linked in Schoology. So if you need to go back and look at any of these sections, we're going to continue on Wednesday with gamma radiation. All right, we will finish up gamma radiation. The shield, Chloe, the shield for beta rays is a thin board such as aluminum, or a few centimeters of air. All right, so if you've gotten the beta radiation column done, you're good.